All right, welcome to the Explainer. Today we're going to break down the fundamental principles of machine learning. And we're basing this on the foundational textbook, Understanding Machine Learning from Theory to Algorithms.
So let's just dive right in, shall we? Because this question, it's really the central puzzle of all of machine learning. It can feel like pure magic, right? That a computer can somehow learn on its own. But it's not magic. It's actually built on a few really brilliant core ideas, and we're going to unpack them.
I mean, you see this stuff in action literally everywhere. It's what lets your phone get what you're saying, what keeps your email from being a total mess of spam, and it's even helping cars avoid accidents. And in every one of these cases, the patterns are just way too complicated for a person to sit down and write rules for every single possibility. So instead, we have to teach the machine to find those patterns itself. Okay, so here is the really crucial point. For a machine to actually learn, it can't just memorize the exact examples it's seen before. That'd be like a student who just crams the answers to last year's test, but has no idea how to solve a new problem. The real goal, the whole point, is for the machine to be able to handle new situations it's never seen before. And that ability, that's what we call generalization. Honestly, in the world of machine learning theory, this is the whole ballgame. It is the single most important goal. Because if you don't have it, you don't really have learning. You just have a really good memory. Let's make this real. Imagine you're trying to build a machine that can tell if a papaya is tasty. You'd show it a bunch of examples where you know the features, like its color and how soft it is, and you also know the label. Was it tasty or not? So now when a brand new papaya shows up, the machine can use the patterns it learned to make a really good guess. It's generalizing from its past experiences. So the big question is, how does a machine actually do that? How does it generalize? Well, you can't just let it run wild and look for any pattern imaginable. That would be total chaos. Instead, we have to give it a toolkit, a set of constraints, to help it zero in on a useful pattern in the data.
First things first, and this is a really key idea. We don't let the machine consider every single possible rule in the universe. Can you imagine? That would be totally overwhelming. Instead, we give it a limited set of potential rules to pick from. And in the lingo of machine learning, this set of allowed rules is called a hypothesis class.
So the machine's got its toolkit of possible rules. Now what? How does it pick the right one? Well, it uses this strategy that sounds complicated but is actually brilliantly simple. It's called empirical risk minimization. And all that really means is it tries out every single rule in its toolkit on the data it's already seen, and it just picks the one that made the fewest mistakes. It sounds almost too simple, but this is a revolutionary idea. You're replacing complex human logic with just an automated search for what works best. Now, this all seems pretty logical, right? Almost straightforward. You give the machine some rules, it picks the best one. But this is exactly where we slam into this huge and deeply counterintuitive problem, a real plot twist at the very heart of learning theory.
You might be thinking the end game here is to build some kind of master algorithm, right? One single genius program that can learn any pattern from any data you throw at it. But could something like that even exist? And the answer, which is kind of shocking when you first hear it, is a hard, definitive, resounding no. There is no master algorithm, and there never will be.
Yeah, this isn't just a hunch. It's a mathematical proof called the no free lunch theorem. What it proves is that no single algorithm can be the best at everything. An algorithm that's a rock star on one problem is guaranteed to be a total failure on another. In machine learning, there is no free lunch.
Okay, so hold on. If there's no master algorithm, how does machine learning even work? How does anything ever get learned? Well, the secret isn't about giving the machine infinite power. It's the exact opposite. It's about giving it smart limitations, productive constraints. The key to all of this is something called inductive bias. Now, that sounds super technical, I know, but it's just a fancy way of saying the machine comes with some built-in assumptions about the world, some prior knowledge about the kinds of patterns it should even be looking for. This example from nature makes it so clear. Think about a rat. A rat has a powerful inductive bias. It's basically hardwired to think, hey, if I ate something and now I feel sick, it was probably the food. But it's not wired to think that the food it ate caused a random electric shock that happened later. That built-in assumption, that bias, is exactly what makes it a successful learner. It helps it survive. So to make this all work in the real world, the theory gives us tools to measure the complexity of our rules. You have to find this just right sweet spot.
If your rules are too simple, you'll miss the real pattern. But if they're too complicated and flexible, the machine just ends up memorizing the training data instead of actually learning. And controlling that complexity, that's the whole game.
Okay, so we've just been on a whirlwind tour through the absolute bedrock of machine learning theory. What's the one big idea you should walk away with from all this?
It is not magic. The real power of machine learning comes from this incredible, carefully engineered balancing act. It's a trade-off between the assumptions we build into the system, its bias, and the flexibility we give it to discover new patterns from data. That delicate balance is what lets a machine look at just a limited set of examples and start to make sense of our incredibly complex world.
And this leaves us with a really important final thought. Since every powerful learner needs a smart set of assumptions to work, the future of AI isn't just about more data or faster chips. It's about a much deeper question. As we build these ever more powerful systems, what are the biases, the poor assumptions about the world that we choose to give them?